Okay, gang. Let's see, I think I'm recording. And I want to give you just a rapid overview here about some of the issues in week 8. Specifically, material in 5.1, 5.2, and 5.3 of our textbook. Launching right into this, 5.1 has some material on function operations. And if I give you an example, like two functions, f of x equals x squared, simple parabola, and g of x, x plus 5, there's a line, basic line of slope 1 shifted up 5 units. And then I give you an expression like f plus g of x. Actually, that function, that operation between functions, is understood pretty well by most people without a definition. It just means f of x plus g of x. So in the example, this would just be the formula you get by adding these two formulas together. So if f of x is x squared and g of x is x plus 5, f plus g of x is the function x squared plus x plus 5, right? Just add the formulas together. And similarly, probably wouldn't even have to write it down, f times g of x is just the product of the two formulas. Let's see. I could simplify that to x cubed plus 5x squared. See what I'm doing? Just multiplying the two formulas together. Okay, but now we want to add an important definition, function composition. Composition of functions, which is really a new operation between functions. Definition, f composed with g of x. So now instead of a dot like I'd use for multiplication, this is an open circle for f composed with g, or the composition of f with g of x. This is defined to be f of g of x. So one function, g of x, is actually the input for f of x. And in effect, what this usually means, what this always means, is you put in an input into this composition, and first you do g of x, and then you take the result of that, and then you input that into f. To just draw a picture of what's going on with function composition, if I draw a picture of a function as an input-output machine, where you throw in x, and then you see what comes out the back end, and I'm trying to draw a picture of what happens with f composed with g of x. Basically what's happening inside is we're running the input through the two functions in order, one after another. But it's a little bit counterintuitive. F composed with g of x is not f followed by g, it's g followed by f. You actually do the inside or second function first. So inside the machine of f composed with g of x, first the x is going to drop into g, and what's going to come out of that, here's your x going into g, is going to be g of x, the output of the g function. That will go into f, and then what will pop out here is f of whatever that is, f of g of x. Okay, so in the specific example, x squared and x plus 5, these two functions, f composed with g of x, if you want a function formula for that, just apply the definition step, and that's really good advice throughout different types of problems with compositions, is to write that definition step, change it from the composition operator to f of g of x. And then the next good piece of advice is think about the inside function first, because that's the first one that happens. So first ask yourself, what's g of x? That's this little linear function x plus 5. And then the last step, okay, now we input that formula into f. And what's f? F is the squaring function. It takes anything you give it and spits out the square of that thing. So I'm going to get out the square of this stuff, and I could simplify that to x squared plus 10x plus 25. So that's a formula for f composed with g of x. Interesting to look at g composed with f of x, the composition in the other direction. So that's defined to be g of f of x. Work from the inside out. So first of all, worry about what f of x is. That's the squaring function, x squared. And then figure out what g of x squared is. So what's g? G is this linear function x plus 5. I put the input of x squared in it. I just put that in place of x, and I get x squared plus 5. Note that the function formula for g composed with f of x is not the same as the function formula for f composed with g of x. In general, composition is an operation that is not commutative. You can't assume that f composed with g will be the same as g composed with f. And another way of thinking of that is the order in which you do these functions can impact what the final output is. Let's go on to another page, and let me check to see that you are still seeing all of this on the screen. It looks like this is working. Okay. Let me go on to another example with a function p of x equals square root x, principal square root x, or radical x, and t of x is a little rational function, 1 over x minus 2. Okay? And let's do a couple of things. Let's find t composed with p of x and the domain of t composed with p of x. Actually, let me note domains before I go on. The domain of p of x, let's see, square root x, I need this input to be non-negative in order for the output to be a real number, right? So the domain of this is going to be, let's see, 0 to infinity. All non-negative real numbers would work here, 0 or bigger. And for t of x, this rational function, the domain would be, let's see, I have a little problem dividing by 0 if x is equal to 2, right? That would actually be a vertical asymptote of this rational function. So the domain would be all real numbers except 2, right? Okay, so let's first of all, kind of reviewing what we were doing before, find t composed with p of x. And again, write the definition step. Then look at what the inside function is, t of radical x. Then input that into the t function to get 1 over radical x minus 2. And then part B, as my math lab will ask pretty often, find the domain of the composition. And there are a couple of approaches to this, and I'll kind of talk through it the way I'm cutting some stuff off here. Yeah, I am. Hopefully that's still visible. Let me talk through this the way the book does. What they say is observe that since this is t of p of x, if you want to have something be in the domain of t composed with p of x, first of all you have to worry about p of x, because the first thing the input does is hits the p function, and p only has domain of 0 to infinity, so you got to be in there, right? If you're in some value, if you put in some value that's excluded in the inside function in p of x, you're going to run into a problem right away. So I know that I need my x to be, you know, let's see, part 1 must be in domain of p to be in the overall domain. So I know I have to be must be in 0 to infinity. But then I have a concern about the t of x. It's got a domain of all real numbers except 2, and you might think you could just exclude 2, which is in this. But 2 is not a problem. If I put 2 into the composition, I'm going to get 1 over square root of 2 minus 2. Square root of 2 is a perfectly good rational, irrational real number. And I'll subtract 2, and I might get a negative value, a not very nice one, but I do get a real number. The problem is, if I put something into P that then produces as an output this excluded value of 2. So for instance, x equal 4 is going to be a problem here, because if I put 4 into P, I get square root 4, which is 2, and then that goes into the t function, and I get 1 divided by 0 is undefined. So I know this is complicated to say. It's actually easier to do when you get the idea. To be in the domain of the composition, it's got to be in the domain of the inside function, and then you also have to exclude values that produce p of x's that don't work in t of x. Ugh. So I need to be in 0 to infinity, but I also have to exclude the value 4. And basically I'm getting that by taking p of x, set p of x equal to excluded values in t of x. So set radical x equal to the 2 that I can't have in t of x, and I find that x equals 4 is a problem. So my solution, my domain is going to be all of these guys, not including 4. So actually domain of t composed with p of x is equal to everything from 0 up to 4, excluding 4. And I'll use a union symbol, plus everything from 4 to infinity. That's such a complicated explanation that kind of is the way the examples are in my math lab in the book. Another thing you can do is just form this composition formula and then very carefully think through what values would be in this domain, and you can kind of see they have to be non-negative because of the radical, but you also have to exclude 4 because that would make you divide by 0 overall. Okay, some kind of tricky questions in there, as you can see. Alright, ready to move on? Let's go on and talk about some of the issues in section 5.2, which includes one-to-one functions and inverse functions. And again, let me see if I'm still somewhat on target here. Okay, so first of all, the idea of one-to-one functions. Let's see, recall, basically when we define functions, an input-output relation is a function, way back when, if each input has exactly one output. That's different than the way the book words it, but I'll kind of give you this version. Basically, the idea with the function, as you'll very well recall now, was that you'd look at the domain, and if the domain was 1 and 2 and 5, then you'd look at the range, and if 1 went to 3 and 2 went to 3 and 5 went to 7 in the range, that would be a function because each of the inputs had one and exactly one output. You couldn't have the branching go the other way, right? If 2 had outputs of 3 and 7, if the branching opened up from the domain to the range, that would not be a function. And we also looked at this in the context of graphs, and we said, you know, for instance, for a parabola, this would be a function because it passes the vertical line test, right? The vertical line test. If no vertical line cut the graph in more than one place, then every input has just one output, and it's a function. Okay, so now we want to look at this more exclusive group of functions. A function is one-to-one, a one-to-one function, if, and I just want to turn this requirement around, if each output has exactly one input. So here, if my domain was 1, 2, 5, it would not be okay to have both 1 and 2 have an output of 3. I'd need to have distinct outputs. So the arrows just go straight across. Let's see, for a graph, this would be a horizontal line test. And so for instance, that parabola that I looked at, if a horizontal line hit two different places on here, this would not be one-to-one, right? Because it's showing me two different inputs there and there that have the same output on the same horizontal line. Horizontal line test. So examples of one-to-one functions that in our toolkit, you know, for instance, the bad graph. Remember the reciprocal function? This would be both a function because it passes the vertical line test, but also a one-to-one function because it passes the horizontal line test. Okay, continuing on, let's talk about inverse functions. And are we still on camera? Yep. Okay, so inverse functions, let's see. For a one-to-one function, how shall I put this? The relation that just reverses the roles of input and output is also a function. Well, what do I mean by that? Well, if you have a relation that's one-to-one, right? The arrows go straight across like this, then you could also just reverse the arrows and you still would have exactly one output for each input and you'd still have a function. So for a one-to-one function, if you just reverse input and output, you still have a function, and this is called f inverse of x, or written this way. Looks like an exponent, but it's just convention that you use a little -1 there to say f inverse of x. And basically this will be the backwards function, or the function that undoes f. And for an example, suppose f is, say, a nice linear function like 3x minus 2, f inverse of x would be x plus 2 divided by 3. Now, this function triples the input and then subtracts 2. The inverse would therefore do inverse operations in reverse order. So this one triples and subtracts 2. This one would add 2 back and then divide by 3. See how that kind of undoes the function? This one could also be written as 1/3 x plus 2/3, making it kind of clear that this is also a line. And if I graph these two inverses, you're going to see an interesting relationship between in the graphs. Let's see, 3x minus 2 is a line with an y-intercept of -2 and a slope of 3. Let's see, this would look like this. Sorry if it's a little bit rough. That's f of x. And this guy, the inverse, is 1/3 x plus 2/3. Let's see, that would have an intercept at 2/3 and a slope of 1/3. Basically like this. Oh boy, that's terrible. That's f inverse. An interesting point about inverses, if this one has a point 0, -2, then the inverse will have a point -2, 0, because they just reverse x and y, right? There'll be a point on f, for instance, 3x minus 2. Let's see, I think 2, 4 is a point there, right? Input 2 and you get 6 minus 2 is 4, yeah. So 4, 2 will be a point on the inverse. And interestingly enough, what this means is that if you just look at the line y equals x, the inverse function, a function graph and its inverse will be balanced on that line. So if I have that line straight up and down, here's f. F inverse will just be the reflection of f across that diagonal line. A couple other things I need to do with inverses that you're going to hit in the homework. You'll have a lot of examples where you have a function formula, and how about if I use something a little more complicated? I've got some examples written for me here. Or I don't. Let me look at the function g of x equals 1/x minus 5. Okay, so that's just a little rational function, right? And my math lab will give you a function like that and say find g inverse of x, find the formula, a formula for g inverse of x. Okay, and the steps are, first write this as an equation. Get rid of the function notation and just write it with y's and x's, okay? And then reverse the role of x and y. So I'm going to write this x equals 1/y minus 5. Minus 5. That's the inverse step, right? Inverses just reverse the role of input and output. So if you just write y as x and every x you see in the formula write as a y, basically here you have an equation of the inverse. And the hard work is just writing this more like a function formula. To do that I have to solve for y. So let's see, I'm going to take a reciprocal of both sides. That's a really handy step a lot of times. You could also multiply both sides by y minus 5, but taking a reciprocal of both sides is really handy. And then I'm trying to isolate y, so if I added 5 to both sides, I'd get y alone. Good. And then finally, I'm just going to write this in function notation. So this means that y, that's my g inverse of x now, is 1/x plus 5. Actually, you might be able to see this coming. G is the function that does 1/x minus 5. G inverse adds the 5 back in and then takes the reciprocal. But maybe it's a little bit less clear to see in a notation formula like this with a rational function. One thing you could do, if I had a little more time, I might put this in the calculator and look at these two graphs, and what you'll find is that they'll be reflections of each other over that line y equals x. Okay, last thing I want to do in this video, if I can squeeze it in, is to just say a little bit about section 5.3 exponential functions, the last new MyMathLab homework, except for the test review. And here we look at, I'm just going to give you some examples. We're going to look at functions like f of x equals 3 to the x. This is a new class of functions, and what's new about it is the x is up in the exponent. So examples of, other examples of exponential functions, g of x equals 1/3 to the x, will generally have positive exponential bases for exponential functions, but they might be fractional. Or h of x equals 5 raised to the x plus 1. As long as you've got variables up in the exponent, this will be part of the family of exponential functions. And let's see. Then here's a non-example. You know, don't say that t of x equals x plus 5 plus, or x to the 5th plus 1. That's not an exponential function. And people will say, well, there's an exponent, but it's a numeric exponent instead of a formula or variable exponent, right? So that one, in fact, you'd recognize as a polynomial. What do the graphs look like? Well, f of x equals 3 to the x, if I point plot it, and I want to do this really, really quickly, so just consider what happens when you put in -2, -1, 0, 1, 2, and look at f of x. You'd get 1/9, 1/3, 3 to the 0 is 1, 3 to the first power, 3 to the second power. I'd get 1/9, 1/3, 1, 3, this would be up at a height of 9. I'd basically get a graph that looks like this, asymptotic to the negative x-axis, and then this direction actually increasing on its entire domain, which is the real numbers, but increasing very quickly in the first quadrant. If you look at this function instead and point plot this, you'll actually get the reflection of this graph across the, this would be g of x equals 1/3 to the x power. You get the reflection across the y-axis. So these basic exponential functions, they basically have this shape or this shape depending on whether the base is fractional or bigger than 1. And let me just draw that out. So if you've got a exponential function f of x equals a to the x power, and a is bigger than 1, you'll just go through the point 0, 1, because anything to the 0 power is 1, and you'll go through a point 1, a, because a raised to the first power is a, and it'll be asymptotic to the negative x-axis and grow very fast over here. Or, if I draw the reflection in here, if g of x is equal to a fractional base, I'll just write 1 over a to the x. I'll still go through 0,